Hello guys, welcome back to Maison African Motives, still on industrial electronics N3, working with revisions. So in this platform, we shall be focusing with the full paper from the June 2022 question paper from your request, guys, so that we can be revising towards our exams, which are ahead of time. So we've got our instructions, which is very, very important for you to read and understand, especially the answers to be given to 3 decimal places, and also that all calculation must include the following 3 steps: the formula that you're going to use, the replacement of values, and the SI unit, and that is the answer in the SI, correct SI unit, and to use pi as 3.14, of which you can use that one of your calculator, but use the 3.14 if possible. All right. On question number 1, we are given various options are given on 1.1, where answers to the following questions. Choose the answer and write only the letter A to D next to the question number. The energy on 1.11 in a balanced atom is equal to the sum of energies of the atom's electrons. All right. Electrons have different energy levels, and an electron's energy level is proportional to the what? All right. So they're asking in this case, what is an electron's energy level is proportional to what? Okay, so it is proportional to the distance from the nucleus. That is on B. All right. So that is what we had on 1.12. The value of the unknown current I2 in Fig 1 is equal to. All right. Remember from your Kirchhoff's law, the sum of currents that are flowing into the junction, that is towards the junction, are equal to the ones flowing away from. So that is the ones flowing into are equal to the sum of the currents flowing out from the junction. So we've got I1 and I2, they are flowing into towards the junction. So which means if we add I1 plus I2, we must obtain I3, which is going out. All right, so this is equal to I3. So we want to calculate I2, so that means I2 is equal to I3 minus I1. So you can transpose I1 to the other side is going to be a minus. So that means we can subtract the 2. So I2 is equal to I3, which is 3,9 milliamps, minus I1, which is 2,5 milliamps. So this can give us I2. So 3,9 minus 2,5, this is going to be 1,4 milliamps, which is 1,4 milliamps is on B. So the answer is going to be on B. That is the best answer that you have. All right, on 1.3, 1.13, field effect transistors, which is FETs, current operated semiconductors devices. Which one of the following statements is not a characteristic of a FET, of an FET? All right, so which one is not a characteristic in this case? All right, and FET is no offset voltage. This is true. And FET is in FET, that is FET, or can just save it as a FET, is a small gain bandwidth. All right, a small gain bandwidth, which is also true. It has a very low input impedance. This is not true. All right, it provides considerable terminal stability, which is true. So the answer there is supposed to be a C. All right, so we are going to have it on a C. We move on to the other part of the question, that is on 1.14, where we are given an SCR, that is a silicon controlled rectifier, is an ordinary diode in injection in conjunction with a control element. Which one of the following is not a use of a silicon controlled rectifier, which is SCR? So we are given various answers here. Light dimming, we can actually use it for that. AC motor speed control, we can use it for that. Heater control, which is also true, but for rectification, no. So this is actually wrong. All right. Then we have given Fermi levels are energy levels associated with the center of gravity of the conducting electrons and holes, which are compactable with their energy. Which one of the following is a representation of a p-type material, a p-type material in this case? All right, so we've got our conduction band, then the Fermi level. Here we've got our valence band on A, which is actually not the one that we need. So we've got our conduction band, the Fermi level on top. No, no, no. So this one, the conduction band, the Fermi level, the valence band, which is not like that. So the Fermi is supposed to be down with what? With the valence band like this. All right. So this is the one that we are going to have. The last one is the one that is best to describe this one. All right. So I think if you are to work with your theory, guys, the more we revise our theory, industrial electronics, to be honest, you need to work with your theory. Because the more you understand that theory, it is going to be easier for you to attempt these typical questions. All right. Indicate whether the following statements are true or false by writing only true or false. Okay. In a parallel resonant RLC circuit, the total current is maximum. This is false. Remember, our current is equivalent to the voltage over the dynamic impedance, which is giving us a maximum a dynamic impedance that what we have. So which means the current is going to be minimum. It is inverse with this one. This one is big, which is max. This is going to be minimum. All right. So this is wrong. It's supposed to be minimum. So this is actually false. If the reverse voltage across a varactor increases, the capacitance will decrease. This is absolutely true. Absolutely true, or actually true. All right. A thermistor is a device of which the resistance changes with change in temperature. That's true. A thermistor, it works with temperature. That's where we have got the NTC and the PTC. Those are thermistors. They work with temperature, positive temperature, negative temperature. They work with temperature. A voltage follower op-amp gain is a very high. It's low, not high. It is low. So this is actually false. In a series RL circuit, the inductive voltage leads the current. The inductive leads the current, which is true. So we can take this from our civil, like this. All right. So if we are dealing with an inductive, this is where we have got inductance here. So we have got inductance on this part. This is our inductance. So voltage is on top. Voltage leads current. Okay. Voltage leads current, or current legs. In a capacitance, if you are dealing with a capacitive circuit, current leads voltage. Current leads voltage. So you can take it from civil. So that part is actually true. All right. So that's it. That's it for this part. We are given choosing from the term in column B that matches the one that is in column A, this description. So we are given the first part on 1.31, maximum reverse voltage that can be applied across a diode. What is the maximum reverse voltage? So this one, it's a peak inverse voltage, which is F. So this one, it's F. The maximum specified current that can flow through a diode at a specific time. This is the surge current. In this case, the maximum specific current, that's our surge current, which is G. All right. On 1.33, the maximum current that can flow through a diode under forward biasing condition, that's a forward current, which is on A. So this is A. The maximum voltage allowed across a Zener diode when used as a reference source. What is that maximum voltage that is acquired? It's a reverse breakdown voltage. Reverse breakdown is a breakdown voltage, which is reverse breakdown. So you see, it's also a repetition. If you check one of the question papers that I have done, you see that also this part, they're actually repeating now and again. On 1.35, current at a reference point of a Zener diode is referred as a Zener current, which is D. So this is a Zener current. 1.4, or we are given a list of values that we are going to use on our answers in this case. Or no, 1.41, we are given that the ratio of the input the ratio of the output signal to the change in input signal of a measuring instrument. What is that? The output to the input, that is the sensitivity of that instrument. All right, so we've got sensitivity. All right, so this answer is sensitivity. So that's our 1.41. So you're going to write sensitivity. 1.42, the smallest change in measured value to which an instrument will respond. The smallest, it's a resolution. The smallest change, that's a resolution. We have got resolution. Yes, we've got resolution here. So our answer is going to be 1.42 for resolution. You are going to answer resolution here. 1.43, indicate how a constant, indication of how constant the indication of a meter will be when connected to a constant source, that is the stability of that instrument. So it is the stability, which is this one. So this is the answer for 1.43. All right. 1.44, the what is oscilloscope is equipped with the 2 electron guns. Which oscilloscope is that? That's a dual beam oscilloscope. All right. Do we have a dual beam? Yes, we've got a dual beam here. So that's 1.44. So a dual beam oscilloscope is equipped with the 2 electron guns. All right. Errors that occur between because of variations in the environment and in the instrument itself. Which errors do we call that are caused by environment? These are systematic errors. Systematic errors. All right. So that is for 1.45. We are going to have this on systematic as your answer for this one. All right. So I think that's what we had on section A, having a total of 20 marks, everything on section A. That's 20 marks for that. And we move on to section B, which is now question 2. It was a comparison of DC theory and AC theory at the same time. All right. So this is what we had. We were given fig 2 below shows a series parallel circuit with the aid of Kirchhoff's laws. Answer the questions that follow. So these are the questions to determine the equation of the loop A, B, C, and so forth and so forth. Okay, so let's see what we have. So the actual part here, you see there's a VT here. So the diagram, you're supposed to have your closed diagram like this to this point like this, all right, to this point like this. This is what we're supposed to have due to the flow of current in this direction. So that is what we're going to have like this, okay? So we are given now to determine the equation that is going to affect the equation of loop ABC. ABC. This is A to B to C. All right. So this is A, B, C. According to A, B, C, we are going to apply this at 0. All right. But I want you to check how this was actually given. This was given not as A, B, C. It was given as A, D, C. That was the actual part that was supposed to be asked. This was supposed to be A, D, C. All right. So what we are going to do, we are going to attempt another part using the actual ABC, taking the ABC as it was, but this was supposed to be A, D, C. This one, A to D to C. This one with the voltage source that we are given, ADC. This is the loop that we are given, this loop of ADC. All right. So from this loop of ADC, if we are to take, I'm going to take it this way. All right. I'm going to take it this way, like this. This is my loop. So this is the flow of current from this positive, this direction, meaning to say, so like I said, this is 2.1 ADC, not ABC. So I'm going to work this one on a separate question with ABC. You will see that we are going to obtain the same thing, but in this case, I'm going to correct that to ADC as it was given. All right. So this is our loop ADC. That is back to A also. So it's going to be to A. So the voltage, remember from your Kirchhoff's law that the voltage, which is this voltage source, is equal to the product of current and resistance across the loop, across the branches that you're given. So if you are to start from this branch here from A to C, we have got current 1 and resistor 2. So we're going to have the product of current 1, resistor 2 in the same direction, is flowing in the same direction. So it's a positive. Then in the same branch, in this branch of C to D, we have current I1 plus I2 are already given. From this I2 and I1, they meet at this point. So this one is going to add. So it is going to be plus R4 into I1 plus I2 like this. All right. So our VT24 is equal to I1 R1, which is I1 R2. So R2, we have R2, which is 22 times I1. So this is going to be 22 times I1 plus, we are maintaining, so it's a plus. R4, we have the value for R4, which is 20. So it's going to be 20 into I1 plus I2 like this. All right, so we are going to formulate an equation from this part by expanding the brackets and collect like terms. We're going to have 22 I1 plus 20 times I2, 20 times I1, which is 20 I1, 20 times I2, which is 20 I2. So collecting like terms, we are going to have 22 I1 and 20 I1 added together. So this is going to give us 44. So we are going to obtain 42, not 44, but 42 I1 plus 20 I2 like this. All right. So this is from the voltage source, from the loop ADC, from this loop, but you take the direction, you take it from the positive side. So I took it, this one, from the positive side. So like I said, I'm gonna come back with another video with ABC so that we see, is that going to give us the same thing even if you were to work it that way with ABC? We are going to have the same thing. All right, now we move on to the other part of the question, which is to determine the equation of the loop A, B, C, D. So it's A, B, C, D, which is now we are looking into this part here, the outer part of the diagram. I want us to check from our diagram properly. All right, so I'm going to remove this part here. It's not affecting us this time. So we are given this as A, B, C, D, which means we are moving from A to B to C to D. That is like this, which means we are referring to the outer part of the diagram. You are moving in the outer part of the diagram, having the voltage source as our VT, this one. So meaning to say, we are going to have this as, let me just have it aside here. So this is our 2.2. So 2.2. So we are taking this from loop A, B, C, D back to A. All right. So back to the point A. So if we are to check here, let's trace what we have for the voltage source, which is our VT in this case. So our VT is going to be product of current and resistance through the branches that the current is flowing with. So I2 is affected here with R1 and R3 in the same branch from A to B to C is the same current which flows. So you combine these resistors under I2, which is R1 and R3. So you're going to add R1 and R3 together. Plus, we still maintain the same direction from this point of C to the point A. We are maintaining the direction of current with I1 and I2 flowing now in this branch. This branch, we are now having another current, which is I1, I2, multiplied to R4. So it's going to be R4 into I1 plus I2 like that. All right. So that is what we are going to have, or just I1 plus, okay, this is I1 plus I2, not R2. This is I1 plus I2, current times resistance, all right, times the resistor R4. So you work with the branch from C to A. This is the same branch which has got I1 and I2 as the current that is flowing in that branch, but there is only one resistor that is there. So you can substitute our values. 24 is equivalent to I2 into R1 and R5, R3, we add 22 plus, that is 12 plus 15 in this case. So you're going to have 12 plus 15 times I2 plus R4, which is 20. So this is going to be 20 into I1 plus I2. All right. So you have formulated an equation. So you just have to simplify further this equation in simplest form so that we can have an equation that we are going to use on our final answer. So that's 24 is equal to 12 plus 15, which is 27. So this is going to be 27 I2 plus, if we expand the bracket, 20 and I1, that's 20 I1, 20 and I2, which is 20 I2 in this case. All right, so that's 24 is equal to 20 I1. So we have got like terms in this case. So this is going to be 27 I2 and the 20 I2. So if you add 27 plus 20, you're going to obtain 47 I2 in this case. So we have got we have formulated an equation from loop A, B, C, D, which is going to be solved together with the first equation so that we can calculate the value of I1 and I2 as stated on 2.3 now to determine the value of I1 and I2. So from the first part of the equation, this is what we had. I'm going to take the first part of the equation, starting with the variables, all right, so that we can solve these two equations that we are given in this case. So that's 2.3. The first equation from this part here, this is what we had, 42 I1 plus 20 I2, which is equal to 24. So I'm going to write that one as it is. That is 42 I1 plus 20 I2 is equal to 24. So this equation is in your hands. You can do whatever that you want in this case. You can even reduce your equation. Like in this case, I can choose even to reduce by 2, by 2, by 2, by 2, just to work with smaller values. So by 2, this is going to give us 21 I1 plus this one is going to give us 10 I2, which is equal to 2 into this one, which is going to be 12. All right, so you can even use it like that with 12. All right, so that is what I'm having. I can even reduce. Then this one, we can't reduce this equation, so I'm just going to take as it is 20 I1 plus 47 I2 as it is. So this one, we can't reduce anything in this case. I'm just going to rewrite as it is. So it was given as 20. So that was 20 I1. So we've got 20 I1 plus 47 I2, which is equal to 24. Okay, I was just supposed to write down here, but still it's fine. So these are the two equations that we are dealing with in this case. So depending with whatever part you're going to solve, either by elimination or whatever method that you're going to work with, depending with what you want in this case. So in this case, let's say I want to calculate I2. I'm going to eliminate I1. So in this case, I want to eliminate I1 in this case. So for me to eliminate I1, I have to interchange these two, multiply with these two. I'm going to multiply on top with 21. I multiply below with 20. So the values that I'm using to multiply, I multiply everything by these values, meaning to say 21 is going to multiply everything on top of this equation one that we have. Everything is going to be multiplied by 21. That's 21 times 20, which is 420 I1. 21 times 47, which is 987 I2, is equal to 21 times 24, which is 504. You multiply every part of this equation. Equation 2, you do the same by 20. 20 times 21, which is going to give us 420 I1. 20 times 10, which is going to give us 200. So that's 200 I2 is equal to 20 times 12, which is going to give us 240 in this case. So from these two equations that we are given, we can see that now I1 and I1 are the same. We are having 420, 420. These are same signs. If the signs are the same, you simply subtract. Whether it's a minus and a minus, as long the signs are the same, you subtract your equations. So meaning to say, I'm saying this is my equation 1, this is my equation 2. So I'm going to have equation 1 minus equation 2. So that's what I'm going to have in this case. So meaning to say, if I am to subtract, that's 420 minus 420, that's a 0. I've eliminated I1. I1 is no longer part of my equation. I move on to 927. With this sign, it's a plus, so it's 987 minus 200, which is going to give us 778, 777 in this case, not 78. All right, if we are to subtract, all right. So let me also have this one aside. That's 777. Okay, that's this one is going to be 7 8 7 like this, okay? I2, which is equal to, if you subtract 540 minus 504 minus 240, this is going to give us 264. So you can divide by 787 by 787. All right, so this is going to give us I2 in this case. If you use your calculator properly, this is going to be 0.335 and so on. So 335, okay, amps. So you can even round off and even write as milliamps if you want, or you can just leave your answer at this stage like this, all right? So with this current, you can substitute this into any of the given equations. You can just substitute or make whatever current that you want the subject, all right? So depending with the equation that you want, if I'm going to take the second equation, 21 I1 plus 10 I2 is equal to 12. So you're going to substitute and make, or you can just make I1 the subject, or you can substitute. In this case, that's 10 times I2, which is this value that we got, 0.335 is equal to 12. So that's 21 I1 is equal to, if we transpose, this is going to be a minus 10. It was a plus, so it's going to be a minus 10 times 0.335 like this. Then you divide by 21 both sides. So meaning to say I1 is going to be equal to, so you divide by 21 here, you divide by 21 this side. So this is going to give us the value for I1 in this case. So make sure that you apply or you use your calculator properly. So this is going to give us something like 0.411, something like that, 4119 and so on. So this is to 3 decimal places going to be 412 in amps. All right, so this is your I1 in this case. So you have to be careful, guys, in your simplification. So if there's any other part which is not clear or any calculation which is not clear, let us know, guys, on the comment section so that we can redo the question together. If there is any other part or any mistake that we had in the simplification. But like I said, I'm going to redo this question working with the A, B, C as it was given, all right, so that we can just see how it was supposed to be in that way. All right, on number 2.4, we are given now on AC theory. We have got a parallel circuit, series and parallel, which is LRC circuit. Like this one, we've got the resistance, inductance, capacitance, the voltage, and this is at resonant, because the first part we are asked to calculate the resonant frequency, which means this is at resonant. Okay, so if it is at resonant, I actually talked about this type of equation before. So if you were watching our videos before, you can have this in mind or in consideration. All right, so this is 2.41. Remember that from your formula sheet, you are given also the formula for resonant frequency, which is 1 over 2 pi, the square root of LC, which is the product of L and C. So that's your resonant frequency is equal to 1 over 2 pi times the square root of, so you can substitute the values that you are given for L and C in this case. So L, that's 10 millihenries. Remember, milli, that's times 10 to the exponent of minus 3 times the capacitance, which is 0.2 micro. So micro, that's times 10 to the exponent of -6, all right? So applying or using our calculator properly, this is going to be 3,558,8127 and so forth. So the 7 is going to change the 2 into 3. So this is going to be 813 in hertz. Remember, resonant frequency is measured in hertz. All right, so that was our first part of the question. Then the other part, which is 2.42, calculate the dynamic impedance, which is ZD. So the dynamic impedance can also be calculated, remember, also from our formulas we are given, that's 2.42. The dynamic impedance is given as L over RC. So that is, it is equal to L, your inductance in millihenries, that is 10 times 10 to the exponent of -3. Then everything over the resistance, our resistance, that is 5, times the capacitance, which is 0.2. Remember, we said that's times 10 to the exponent of -6. All right, so we can simplify this to obtain the dynamic impedance, which is going to be 10,000. So this is going to give us 10,000 ohms, or in kilo ohms. Remember, 1,000 means kilo, so that can be 10 kilo ohm or just 10,000 ohms in this case. All right, calculate the currents through the different branches. Okay, so take note, this circuit is at resonance, and we know that under parallel resonance that these two are equal. The currents, they are equal. The current that is going to be through the capacitor and the current through the coil, these two are equal. All right, so we can have this as all right, so this is 2.43. So we can have this as 2.43. Remember that we said IC is equal to IL. So if I calculate IC, I'm calculating IL. Also, XC is equal to XL. If I'm calculating XC, I'm calculating XL. So depending with the what you are best, or what is best with you or on your calculation, you can calculate XC or you can calculate XL. Still, it's one and the same thing. So as for me, I'm going to calculate XL. Remember that these currents, if you're talking about IC, it is equal to the total voltage over XC, which is the same as XL. The same with IL is going to be VT, which is the total voltage over XCL. But these two, they are equal. That's why we're saying these two currents are the same. So in this case, like I said, I'm going to use XL, which is 2 pi F RL at the resonant frequency. You use the resonant frequency to calculate the XL. Remember, we calculated the resonant frequency before. This is your resonant frequency here. So you're going to use this value. So this is going to be 2 pi times the resonant frequency, which is 3558,813. All right. So times the inductance, our L in this case, remember our L here is 10 times 10 to the exponent of -3. So you're going to multiply times 10 times 10 to the exponent of -3. That's 10 millihenries. All right. So we are going to obtain something like 223. That's 223,607 in ohms. So the same thing that you could have obtained from calculating XC, which is 1 over 2 pi FRC, like this. We are going to obtain the same answer for this value. So that means this is the same. So now to calculate the current, which is for IC or for IL, like I said, since these two are actually the same, then we can use IL. Since we calculated XL in this case, that means IL is going to be VT over XL. So that's VT over XL in this case, which is equivalent to IC. So this is the same. So our VT, that is the total voltage from the circuit. We have got our total voltage here of 220 volts. So this is going to be 220 volts. All right. So let me see what we have here. So we've got 220 volts on VT. 220 divided by XL or XC, which is 223,607. So this is going to give us the value for IC, which is the same as the value for IL, okay? Which is something like 0, that's 0.9838, so which is going to be 84 amps, or you can write in milliamps if you want, or just leave it like that. So that is the currents that you're going to have across the given branches in this case. All right. On the other part of the question, we are now given to calculate the total current of the circuit that we are given on 2.44. Remember, current is taken from the total, that is the impedance, which is the dynamic impedance, the maximum impedance that we can have, which is the dynamic impedance. So you can use it from this dynamic impedance. We can calculate the total current. So 2.44, the total current is equal to the total voltage over the dynamic impedance. Remember, we had the total voltage before, 220 volts from our circuit. So we are going to use the 220. So this is going to be 220 divided to the dynamic impedance, which is 10,000 or 10 times 10 to the exponent of 3 or just 10,000. So this is going to give us the total current of the circuit in amps. Take note about the units that you are using, all right? So IT is going to be 0.022 amps, all right? So you can have it like this, or you can write it in milliamps, which is 22 milliamps in this case. All right, so this was our question. With everything that we are given now, we are given to conclude this with a phasor, to draw a phasor diagram of this information. So like I said before, that if you are to draw a phasor diagram, take note that these two currents are the same, IC and IL, they are the same. So which means we are going to have these in opposite, just in opposite, in a vertical line. So this is 2.45. So you're going to have IC and IL in a vertical line, then the total current in the horizontal line. So this is our IC, which is equal to IT of 0.984 amps. The same with IL, which is 0.984 amps. And our IT, the total current, is going to be to the horizontal, which is 0.022. So that's what we have if you are dealing with a series, I mean a parallel resonant, if they are at resonant, okay? That is what you consider in this case, all right? So this is enough for 3 marks. Yes, you can even write the voltage if you want, but this is enough for the 3 marks that you're given. All right, question 3, we are now given semiconductor diodes and transducers. Voltage multipliers are actually in many ways similar to rectifiers in that they convert AC to DC voltages for the use of electronic circuit appliances applications where it is necessary to have a very high DC voltage generated from a relatively low AC supply. Answer the following questions regarding to voltage multipliers. Draw a neatly labeled circuit diagram of a full wave. Take note, this is a full wave voltage doubler with the following components: a transformer, the 2 diodes, the 2 capacitors. 4 marks for that. All right, so this is what I have, guys, for a full wave voltage doubler, the one that you are actually having with the components. So we are having our transformer here, the 2 diodes that we have, and the capacitors in this case on the other part. All right, so that is the circuit that you were being asked in this case to give or to have. All right, let's check another part of the question, which is on 3.12. 3.12, name one application of a voltage doubler in electronic circuits. So from that voltage doubler that we have, what are the applications? So here I've got 3 applications that you can pick any one from there, because they're just an application. It can be used in televisions, in computer monitors, in oscilloscopes. We can have this as an application. All right, on 3.2, we are given Zener diodes allow for the flow of current when used in forward bias, but they also allow the flow of current when used in a reverse bias. All right, by referring to the Zener diodes, answer the following questions. Draw a neatly labeled sketch of the characteristic curve of a Zener diode. That is 4 marks. Take note, we are dealing with the characteristic curve in this case. All right, so here, this is what I'm having. On your characteristic curve, you are supposed to mention these, especially the Zener knee, and the Zener breakdown, the reverse voltage. So these are the voltages. Then the reverse bias region, the forward bias region, with the forward voltage, the forward current, and the reverse current. So make sure that everything is properly indicated or represented on your diagram. Then on 3.2, we are given to draw the IEC symbol of a Zener diode, the symbol that you use if you are dealing with a Zener diode. In this case, there are so many symbols that you can take, but just refer to any one of these to represent a Zener diode. So what is important is the indication that you are given in this case. All right, let me try to do this, maybe it can be clear. All right, so this is supposed to be, all right, we are having like this, a Z, or you can have it like this, or you can have this Z slanted a little bit like this. It's still representing a Zener diode. All right, so that's what was actually required in this case. On 3.3, we are given an optoisolator is an electronic component that transfers electrical signals between two isolated circuits by using light. By referring to an optoisolator as answer the following questions. 3.1, draw a neat labeled circuit diagram where a diode optoisolator is used to switch on an silicon controlled rectifier. 3 marks for that, as it is used to switch on a silicon controlled rectifier. So this is what we have when it is used in that manner. So mentioning also the voltage, that is high AC voltage, and also the diodes with your silicon controlled rectifier in this case, and VCC. So this is actually 3 marks for that. All right, then the other part, we are now given to draw a neat labeled configuration of a optoisolator using a Darlington pair. What are we going to have on the, if you are using a Darlington pair? So a Darlington pair, these are two transistors which are connected in this manner. So that is what you're going to have on this Darlington pair. Take note, the from the first transistor that we are having our emitter being collected to the base and so forth. All right, so having your high voltages and the first diode, these are now transistors on the other hand. So this can be of 2 marks if the Darlington part is being shown. All right, the 3.4, the capacitive transducers are used to measure gas flow pressure in a jet engine. Describe the operating principle of a capacitive transducer. So this description is the one that they actually need. Yes, you can have your own description, but it is best for you to answer in this manner, that if the distance between the plates are varied by an external force, the capacitance will vary. So it's all about the distance between the plates and the external force being applied. This will make the capacitance to change or to vary depending with the effect that is given at that moment. On 3.5, we are given piezoelectrical transducers use the principle of generating an EMF if an external force is applied to a crystal. Name 3 instances where these transducers are used. When the piezoelectric transducers are being used, which conditions can they be? All right, so here I'm having in sound, dealing with microphones, in acceleration, when you are dealing with an accelerometer, then in pressure, if you're dealing with force, in vibration, dealing with ultrasonic cleaning. So any 3 was actually required. So this was the last part, having a total of 20 marks on this part of our section, or on this part of 3.5, in this case, dealing with the piezoelectrical transducers. All right, so this was the last part, having a total of 3 and 20 marks for this whole part of question 3. On question 4, it's actually again theory part. These semiconductors, transistors, and operational amplifier, this was a combination of 2 combined together. So the first part on 4.1, a transistor is used as an electronic switch by driving it either in the saturation area or in the cutoff region. Give 4 advantages of using a transistor as a switch. So this whole explanation is not of importance. The question is to give advantages of transistor as a switch. What are the benefits? That is the advantages. All right, so in this case, let me show you what I'm having here. We are given it has the small base emitter current, can switch off the transistor on or off. There is no wear and tear on switch gears. It is faster switching time to control. It has got a faster switching time control over long distance, and there are no moving parts. It is noiseless. There is noiseless operation if you're dealing with electronic gadgets like a transistor. All right, so this can be of benefit or an advantage of using transistor as a switch. On 4.2, we are given that a transistor, it has got 3 terminals, the emitter, the base, and the collector. Yes, we know that. So this information, what is the use? Using 3 terminals, the transistor can be connected in a circuit with 1 terminal common to the both input and output in 3 different positions, possible configurations, all right? Then we are asked on 4.1 to compare the input and output impedances of the three different transistor amplifier configurations. Okay, when you are dealing with the transistor configurations, can we differentiate these ones? All right, so remember, we have got the common emitter configuration, the common collector configuration, or it can be a common base configuration. So now you have to talk in terms of the impedance. What do we have in terms of a common emitter? It has got average input impedance. Then at the output, it has got high output impedance. Dealing with a common collector, we have got a high input impedance, low output impedance. On a common base, low input impedance and a very high output impedance. So this is the comparison, or how you can select or to properly give a comparison between these two. Then we are now asked again to compare the phase shift that takes place in the three different transistor amplifier configurations that we had before. What about the phase shift? What is going to happen with these three? All right, so in terms of phase shift, also dealing with the common emitter, the common collector, and the common base. The common emitter has got a 180 phase shift, while is the common collector, there is no phase shift. On the common base also, there is no phase shift. So this is how they can be given in this case, all right? So the other part, we are given to draw a neatly labeled circuit diagram explaining an RC coupling method between two transistor stages. That is a coupling method in form of a diagram. Also, this diagram I showed you guys before, so I think now we are used to this. So I remember that you must label everything properly, the resistors, the trans as it is, like this, guys. 4 marks for that, so you can actually obtain your 4 marks from there. All right, so that is it, guys. On the other part of the question, now we are given to draw a neatly labeled block diagram explaining series voltage negative feedback. Also, this one I gave you before, so it's actually a repetition on this one. So this is what we have in this case. All right, that's our 4.4. We are given an amplifier with the voltage V in and the VF, which is, and we've got V out, which is the output in this case. So with this, we can actually have our 2 marks. So that was our question on the application or drawing a series voltage negative feedback. All right, so 4.5, draw a neat labeled circuit diagram of an inverting op amp. This is an op amp, an inverting op amp. Also, guys, I gave you this one before, so still the same op amp that you had, so whereby you're supposed to indicate the input properly and also showing us the output at the end with the reference that we have, RF with the positive, negative. Okay, that's it. This one I do not have much to explain or to give there. You just need to know your diagrams much. Okay, a voltage follower on 4.6, we are now given that we have got a voltage follower op amp, that is operational amplifier, is also called a unity follower op amp. What is the main property of a voltage follower? So all this part that they're explaining is not important. The question is here, what is the main property of a voltage follower op amp? So the main property that we have, it is primarily used for matching high input, high impedances that we have at output to low input impedance. Okay, so that is a voltage follower op amp is primarily used for matching high impedance, output to a low impedance output, or to a low impedance input. In this case, that is low input impedance or low impedance input, which is the same high output impedance. So you can have it that way, which is easier for your understanding, depending with how you understand this, guys. Then on 4.7, the input wave form that is supplied to a differentiator. So you're given from a differentiator op amp is shown in fig 6 below. Draw the output wave from the circuit. So we need, this is the input wave V in. What about V out? So sometimes they can even give you to draw both V in and V out. All right. So for V out, this is what we are going to have depending with the cycle. Sometimes they can give you the input as maybe we are given as a square wave. This was a sine wave. So we are going to have it as a sine wave in the other part of our output in this case. All right. So if it is a square wave, then we are going to change. I think if we check the question paper of February 2022, I explained when it was given as a square wave. So please make sure that you watch that video so that you can have more on that one. 5.1 on measuring instruments and electronic power control. 5.1, we are given to draw a neat labeled block diagram of a calibrated oscilloscope, oscilloscope. That is 6 marks, a lot that we are having in this case. All right, so this is what we have, guys, on a calibrated oscilloscope. I don't know if this is clear, or let me try to do this. I don't know if it is clear, guys, but I just hope everything is clear. So we have got our, all right, let's see. Okay, so here we've got our V, which is voltage, then the attenuator, then the vertical position, the delay line. Then what is important here is the time-based generator and the trigger circuit. So this part, and also the supply to all circuits, and the supply to the power supply to the CRT. That is the cathode relay tube in this case. So this is your CRT cathode relay tube that you have. So these are the major points that you're supposed to indicate or to show on your diagram in this case. All right. So the other part of the question now on 5.2 was to Fig 5 below. It shows a continuous balance digital voltmeter. Label the blocks by writing only the answer next to it. So sometimes they can even give you to draw this diagram. Now they've drawn it for you. They just want you to label. All right. So 5.21 here. This is our DA converter. So this is the DA to A converter. And we also have 5.22 here, which is our comparator. This is where we have our comparison between the input that you are given. So that's your comparator in this case. So that was the question. So like I said, know this diagram. They'll ask you, refer to Feb 2022. They had a question for you to draw. That is the continuous flow balance of a digital voltmeter. They asked you to draw. Now they've given you. So you must know this diagram from the question papers. This is how they give you from question papers. And also you can take those diagrams that they use. Like you can see how do they draw their diagram. This is also how do they want you to answer when they say draw a diagram for a continuous balance digital voltmeter. You draw also your diagram like this, the same way they present it to you. So this is how we can also learn from them by revising more question papers, as I always say. 5.3, we are now given an silicon controlled rectifier can be considered as a power diode, which can be switched on by a low power signal applied to the control input terminal. Draw a neat labeled characteristic curve. Take note, we are to draw the characteristic curve in this case for an SCR, which is the silicon controlled rectifier. All right, so for this part, this is what I'm having. I want you to see this down, this one. All right, so we must indicate our major points. That is our reverse breakdown region, where we are given the breakdown voltage. Then here we have got our forward breakover voltage, which is in the forward conduction region. All right, then the forward current and so forth. So this is can actually attain us 4 marks for that. So the more we indicate the major points, so these are the major points. So it's very, very important for you to have your major points presented for you to obtain full marks for that. All right, then we are now given on 5.4 to give 2 advantages of a silicon controlled rectifier, that is SCR. So also these advantages I have also given you before. So you just have to take any 2 from these ones that I'm having. That is low on resistance, high off resistance, the rapid switching, and also the low control power, and also the issue of lifespan, that it has got a long lifespan. So any 2 marks can be used as advantages of what? A silicon controlled rectifier in this case. On 5.5, we are given to draw a neatly labeled circuit diagram of a silicon controlled rectifier in a half wave control circuit. The diagram now of an SCR in a half wave. Take note. So it was also all about the silicon controlled rectifier in this part. So this is what we have in a half wave. That is in a half wave, we're going to leave the load, the SCR, which is our silicon controlled rectifier, to the control circuit. So these major points, that's 2 marks. We are supposed to have these as our major points in this case. All right, then the last part of the question, we are given a silicon, that is an SCR, will continue to conduct until it is switched off. Give 2 methods of switching off an SCR, which means you do not just switch off. You have to apply methods that are specific for switching off. So we have got the 2 major methods, which is the reduction of anode to cathode current to below the holding current, and also the commutation method. So these are the 2 major methods which are needed for us to switch off, or to make sure that our silicon controlled rectifier is no longer operate, is now switched off. That is what we have. So that was it, guys, from our section B, having a total of 80, and everything from the whole paper 100 marks. So this is what we need in our revision. Working with more question papers, make sure that you work with more revisions, more question papers, which can actually help you in answering typical questions that you might be given. So it is very, very best that you add more question papers in your revisions. Also referring to your textbooks, the ones that you are using in your current syllabus, with the question papers, so that you see how do they ask the questions and how are you supposed to answer or to attempt such typical questions. For now, that's it, guys, for Maison African Motives. Till we meet again.